So you should by now have worked your way through, or dotted around 10A and 10B, and hopefully you've got 10C done up for today. And I was just saying to Izzy, I wasn't. This 10D is pretty straightforward, but then 10E isn't. So I didn't really want to try and cover both in this lesson. So perhaps with hindsight, I should have done, but I haven't. So I'm just going to talk you through 10D now. But it may well be that you guys want to get on and have a look at 10E independently and make a start on that. Let me know how you're getting on with that. And because our next lesson is Friday. I was just saying to Izzy, there's very few, but one or two questions where you sort of dealing with like weights inside a lift going up or down, or which are quite confusing, I think. But the vast majority is just
we're in school on Friday.
Are you on school Friday?
Oh, yeah, we've got physics.
Oh, right. Okay, Izzy. Right. Oh, well, no, I think in a way then, that's fine. That's fine. I will. Thank you for that, Izzy. I'd forgotten that. So when do I see you after that? I don't see you until Tuesday after that. Well, not to worry. I think the same thing applies. I think I still think if you can get onto 10E, I'll tell you what. Let's just quickly do 10D now, and then we'll just have a quick look at 10E now. We might as well. And I think what we'll do, we'll look at 10E, but just leave out that one particular tricky bit, because that's 90% of it is pretty straightforward. So we'll do that. So let's quickly do the 10.4, which leads us on into 10D. So this is pretty straightforward. All we're doing here is just applying F equals ma, but in a two-dimensional, so in a sort of a vector format. So force and acceleration are both vectors. They've both got size and direction. So F equals ma, both the force and the acceleration of vectors. So I prefer sort of the column format. I think it's easier to see, but all we're saying over here is it's pretty straightforward. If they give you the force being 3.8 and the mass being 0.5, then by definition, the acceleration must be 6.16, because you're just literally just multiplying across. So when in example 8, when they're asking for the acceleration, we are giving it in vector format. Okay, so our final answer is 6.16. As I said, I quite like setting it out in column vector format rather than the IJ format, but there's nothing stopping you doing the workings in a column vector format. But obviously, if they're asking for the final answer in IJ format, you must do so. So that would be the 6i plus 16j. And then for part B, when they're just asking for the magnitude, the size and the bearing, well, that's just GCSE maths. So the magnitude, the size, we're just literally going to Pythagoras. If we're 6 along and 16 up, the actual size of the acceleration is the hypotenuse. And to work out the bearing, well, you start off by working out the acute angle, just using SOHCAHTOA, using tan. And then, of course, remember, a bearing is always measured from north clockwise. So once you've worked out theta being 69.4, your actual bearing, alpha, you take that away from 90. And again, remember that a bearing, you always give the 3 digits before the decimal point, so 0, 20.6. Right, and yes, in example 9, very straightforward. You're just literally adding the 3 forces together. We're told that, so you just literally, again, I would do that in vector format, just add the I components, add the J components. That gives you a net force, a resultant force, and then you're just using F equals ma again. And that does take you into exercise 10D. So I think if you can dot around that and work your way through 10D, the earlier part of this week, I think, particularly given you're missing Friday's lesson, it'd be good to be making a start on 10E. So let's just have a quick look at that now. Okay, so 10E. So what we're looking at here, as it says, is connected particles. Now we have the choice when they are connected of either choosing to look at them as a single whole particle or separately. Okay, so if they're moving in a straight line, so they're just sort of being tautly held together, when we say sort of an inextensible rod or a string, so literally one's pulling the other one along or one's pushing the other one along, they're going in the same line, you can pick and choose and do your F equals MA on either the bit at the left, the bit on the right, or the whole package. So yes, so let's take a look at this question here. So this is the classic example. This is the type of question I would like you to be looking at, please. So let's just read this one through. For two particles P and Q, so P and Q, we're given the masses. They're 5 kilograms and 3 kilograms respectively. They're connected by a light inextensible string. So basically, P is just pulling Q along. Okay, inextensible means it's not stretching. So they're both going to be accelerating at the same rate. And we're told that P is pulled by a horizontal force of magnitude 40. There we go, being pulled along by 40. And we're told that they both experience frictional forces. Okay, now remember, friction always goes in the opposite direction to the motion. So we're going left to right over here. So there's the 10 friction on P going to the left. And there's the 6 friction on Q, also obviously going to the left because the motion is to the right. So that's putting all of the information into the question on the diagram. In addition to the, just to make our diagram complete, we've obviously got the weight of Q and the weight of P, so 5G and 3G. And then we have equal and opposite normal reactions. Okay, we've got a normal reaction here and a normal reaction here. Now, please get used to this idea here. Get onto your diagram straight away. And you may already be familiar with this from physics. I don't know. But when you're being pulled along like this, you've really got equal and opposite tensions here, with the arrowheads pointing to each other. Okay, so you think of it as the whole of Q is basically acting as a resistive force on P. That's this tension here. It's sort of being held back by Q. And you've got the equal and opposite tension here, which is really Q being pulled along. So you can either go and choose to just look at the left-hand side of that dotted line and look at Q as a whole system, or which would obviously include T, or you could go and look at P in isolation, so everything to the right-hand side of a dotted line, which again would of course include T. Or you can just look at the system as a whole, in which case these two tensions cancel each other out. So what we've done here for part A, we're being asked to find the acceleration. If we just go and look at the system as a whole, okay, so we're doing F equals MA, F equals MA. So and we're resolving left to right. So any forces going to the right are positive. So our net force is the 40, take away the 10, take away the 6. That's our net force. That's our F. And that equals our combined mass of 8 kilograms. And we don't know the acceleration. The acceleration is our unknown. So that's going to allow us to work out that the acceleration for the whole is 3. And then for part B, find the tension on the string. Now you've got a choice here. You could go and look at P in isolation or Q in isolation. Okay, so they've gone and chosen to do P. So we're just looking at P in isolation. Again, we're doing F equals MA. I would suggest you write F equals MA as your starting point. So for P in isolation, our forces are a positive 40, take away the tension, take away the 10. That's our net force. That equals our mass of P for 5 and the acceleration of 3 that we've just worked out. So that our only unknown is the tension, so we can work out that tension is 15. And just like they're saying there in the yellow box, you know, if you just do the same workings for Q in isolation, you will also get tension being 15. And then part C, explain how the modeling assumptions that the string is light and inextensible have been used. Well, it's inextensible, so it's not stretchy. It's not like a piece of elastic. So by definition, the two accelerations are the same. The accelerations of both of the masses are the same. And then it's light. So tension is the same throughout the length of the string, and the mass of the string is negligible. Right, so that's the big example. I want us to be doing all the questions that are similar to that, please. This example 12 is the one that I want us to leave for now. So I think there's only like one question in the whole of the exercise which is like example 12. I want to come back to that one, not least because I need to work through that again in my mind. I find those particularly tricky. And then we're on to exercise 10E. So really, I would like you to work your way through 10E, please. So yes, question 1, question 2, question 3, that's all 4. Question 4 is the one for now I would like us to leave. We will revisit that next lesson. I mean, you're welcome to give it a go, but I think that's the tricky one. And then I think everything else from memory is all standard. So 5, 6, 7, 8. Yeah, these are all fine. 9, yes, and 9. So basically, guys, if you could just work your way through 10D, or bits of it, that shouldn't take you long. And then I want your time spent doing 10E, please, but with the exception of question, it's only one question, but with the exception of that question 4, is the other ones I want you to focus upon. Okay, that's it. Any questions, anyone?
No.
Okay, thanks, guys. So 10D, 10E, we don't have a lesson on Friday. Thanks for reminding me that you're in school on physics on Friday. So, and then on that following lesson, that Tuesday lesson, we'll move on, but we'll just have a bit of a look at that that lift question, that one that I don't really like. That was specific example, and that question number 4. Okay, guys, have a good week. Bye.
Thank you.
Bye, Izzy.
Bye. Thank you.
Yeah, bye, Patrick. Bye, James.